Okay, so finally we come to one of the most interesting concepts in Newtonian mechanics, and that's angular momentum. Now we've talked a lot about linear momentum. So this is Newton's quantity of motion, his mass-weighted velocity associated with translational motion. Okay? Angular momentum is similarly the quantity of motion associated with rotational motion. Okay? But instead of having a mass times a linear velocity, we're going to have a moment of inertia times an angular velocity. Okay? Now it's a little more subtle than that. Okay? You'll see. Okay, so I'll just preface this by saying that this is going to be a little bit challenging in two different ways. One is you're going to have to be able to really imagine and visualize things happening in three-dimensional space, and to be able to draw vectors pointing in all sorts of different directions in three-dimensional space. So to be able to draw diagrams that have perspective, vectors coming out of the page, into the page, at angles and all that kind of stuff, and visualize the whole thing. The second thing that's challenging about angular momentum is, is that the math is deeply connected to vector cross product. Okay, so you need to be able to draw these different vectors, and you'll need to be able to work out vector cross products, apply the right-hand rule fluently, and all that kind of stuff. Okay, so I'm going to assume you're all good with the right-hand rule, and you understand vector cross product, and we'll get going. Okay, so we'll start with our sort of generic kind of situation of some object in motion, say an airplane, which is moving around on some trajectory in three-dimensional space. Now, at one instant of time, say the airplane is located there. Now, it's moving in a direction, has a velocity which is tangential to the trajectory at that point, and it has a mass. So it has a mass-weighted velocity, mv, or momentum, linear momentum, p, at that instant of time, t. Okay? Now, when we talk about angular momentum, what's very important is we need to pick and then stick to a particular point in our inertial reference frame. Okay, so for instance, let's choose this point. It's arbitrary where you choose it, but once you choose it, you have to stick to it throughout the entire problem, no matter what's happening with things in motion. That point, that special point that you've chosen arbitrarily, needs to be fixed. Okay, so let's call that point O. Okay, and usually or often, we choose that point O to be the origin of our inertial reference frame. Okay, so here's our inertial reference frame, and there's a special point O in that inertial reference frame. And that special point O will first of all determine the position of the object relative to O. It'll be used in calculating the torques that are exerted. It'll be used in evaluating the angular momentum about that point, and so on. Okay, so we'll talk much more about that. So at this instant of time, where is the airplane? Well, it's over there. Relative to what? Well, relative to O. So it has a position vector, r, at this instant of time, t. Okay? Now we know that as that airplane flies, its momentum is changing. Well, what causes changes in momentum? Well, forces. A force acting over time transfers momentum. Okay? And so we need to think about the forces that are acting. So we need to draw a free body diagram. Okay, so there's our airplane at this instant of time, and there are various forces acting. There's the usual suspects. There's gravity pulling down. There's, say, a lift force going up and a little bit back, let's say. It's moving through the air this way, so there's a drag force in that direction, and there's a thrust force in that direction to counter the drag, etc. Okay, so we've got a bunch of forces acting on the airplane at that instant of time. And those forces acting over time transfer momentum to the airplane, change the momentum of the airplane, okay, as it moves along its trajectory. So the basic law by which that momentum transfers happens is, of course, the law of Newtonian dynamics, the Newton's second law. Okay, so this is the fundamental law of Newtonian dynamics, which says that if we evaluate the net force, add up all the forces acting at some instant of time, so suppose it's this vector here. If we add up all these forces, suppose it's that vector. So that's the sum of all the forces acting at that instant of time. That's the net force. Okay? And that net force causes the momentum to change. Okay? And so that is the net force is equal to the rate of change of the momentum. Okay, in other words, in an infinitesimal time interval dt, the change in the momentum dp is equal to the net force acting over the time dt, net force times dt. Okay, so the impulse delta p theorem is basically what Newton's second law is saying. Okay, so this law is fundamental. And this law is all you need to solve this problem. Okay, so if you know the initial position and the initial momentum of the airplane, and you know all of the forces acting on it, then you can calculate the entire trajectory. So this is sufficient to solve the whole problem of motion of this airplane. Okay, but what we're going to do is something a little interesting. What we're going to do is we are going to take, we're going to form a vector cross product. That's a vector and that's a vector. And so what we're going to do is form a vector cross product of, at this instant of time, the position vector r cross the sum of all the forces. Well, that should equal that position vector r cross the time derivative of the momentum. So we're going to go r cross this side equals r cross this side. And so it's not going to give us any new information about the problem. All of the information about the problem is in that equation already. But if we take the vector cross product of both sides with the vector r, then what it does is it pulls out some and helps identify some really interesting information about the dynamics. Okay? And that's associated with torques and angular momentum and all that kind of stuff. And it identifies a new conserved quantity. Angular momentum is conserved. Just like energy is a strictly conserved quantity, and momentum, linear momentum, is a strictly conserved quantity, angular momentum will be a strictly conserved quantity, as we will see. Okay? So what we want to do is we want to calculate the vector cross product r with the left-hand side of that equation. So this is all happening at an instant of time t. We take the position vector r at that instant of time t, vector cross product with the sum of all the forces at that instant of time t. Okay? Now, r cross the sum of the forces is, of course, the same thing as the sum of r cross all the forces, of each of the individual forces. Okay? And now, what is r cross f? Well, let's see. Let's choose one of these forces. Let's say the gravitational force down. R cross f, that's r, that vector, cross the gravitational force down. Okay, vector cross product, r cross f, is a vector pointing out of the board. Okay, it is a torque. R cross f is torque. So the gravitational force pulling down on the airplane exerts a torque on the airplane about that point. It's a twisting force clockwise about that point. Okay, the lift force, okay, R cross the lift force. Well, the lift force is that way, so R cross F is a vector coming out of the board towards me. It is exerting a counterclockwise torque on the airplane about that point O. Okay, so what we see here is it's the sum of R cross F for all those different forces. So it's equal to the sum of all of the torques that each of these individual forces act. They're all being applied at that point, that's the application point, and they are exerting torques about that point. Twisting forces, clockwise, counterclockwise, or whatever axis, because torque is a vector. Okay, so you can exert twisting forces like this, you can about this axis, you can exert twisting forces like that about that axis, you can exert twisting force about that axis, you can exert twisting forces about any axis. Remember, the direction of the torque is the direction you stick your thumb in, and then your fingers curl in the direction of the twisting force. Okay? So this is the sum of the torques about the point O. That's super important. Okay? This point O will be crucial. Okay? So that's the left-hand side. So we did R cross the left-hand side. Well, that's got to equal R cross the right-hand side. Okay, so R, the vector R at this instant of time, vector cross product, the time derivative of the momentum at that instant of time. Well, let's just drop the t in there. It's all assumed to be at the time t. So it's r cross dp dt. Okay? Now, I want you to remember something basic from differential calculus. So if you have the time derivative of a product of two functions, f and g, that's equal to the time derivative of f times g plus f times the time derivative of g. Okay? So what we can do is we can see, well, this looks like f times the time derivative of g. Well, that'll equal the time derivative of r cross p minus the time derivative of r cross p. Okay? So we can write this as the time derivative of r cross p. Remember, r and p are constantly changing as the airplane is flying around. So this is a vector which depends upon time, and we're evaluating the time derivative of that. So it's the time derivative of the product minus, bringing this over to the other side, minus the time derivative of r vector cross product with p. So minus the time derivative of r vector cross product with p. Okay? Now we look at this second term over here, and well, dr dt, I don't know, dr, this is r at the next instant of time. Dr dt is, of course, the velocity. The velocity is in the same direction as the momentum. They are parallel vectors. So the vector cross product is 0. Okay? Great. So then we look at this and we have something. We know that basic Newtonian dynamics tells us that sum of the forces is dp dt. So it will be true then if we go r cross sum of the forces, that will equal r cross dp dt. So this thing will equal this thing. Okay, so that equals that. Okay, and so we get this sort of an equation which looks like a new equation, and it is a new equation, but it contains no more information than this. Like I said, what it helps to do is identify useful information, some really interesting information in the Newtonian dynamics problem. So what we do is, it says the sum of the torques, so the net torque that all of these forces exert on the airplane at this instant of time about the point O, okay, is equal to the time derivative of something. So that's a really nice law that emerges here. Okay, it looks a lot like this. The sum of forces is dp dt. Here we have the sum of torques is d by dt of this new thing. Instead of p, linear momentum, it's r cross p. Well, let's define a new thing called angular momentum, equal to r cross p. Okay, so what we do is we define, and this is an extremely useful definition because, as I said, it turns out that this thing, angular momentum, is a conserved quantity. It's a very powerful and important quantity in dynamics. Okay, so we define a new quantity, L, and it's a vector. Okay, so this is L is equal to this thing, r cross p. Vector cross product. So the angular momentum of this airplane at any instant of time, the angular momentum about the point O is r cross the momentum at that time. So right now, if you go r cross p, well, it is a vector pointing out of the board. Okay, so the angular momentum is clockwise about that point O. The angular momentum of the airplane is clockwise about the point O. Okay, and so I really want to emphasize this. L is r cross p, but it's super important that we are saying the angular momentum about the point O. So when you put a vertical line there and an O there, it means angular momentum about, evaluated about this point. Not this point, not this point, but that point. Because angular momentum is r cross p, okay, and the r here is the position of the airplane relative to that same point O. Okay, so I'm just explicitly saying this, because if you chose your origin point to be, say, over here, okay, then r is in that direction. R cross p is r cross p is out of the board if you choose O to be there. R cross p is into the board if you choose the origin point to be there. So r cross p is going to change depending upon your choice of origin point. Okay, so what you have to do is pick an origin point, pick a point about which you are evaluating the angular momentum of the objects in motion, and stick to that point throughout the entire dynamics. Okay, you can't move that point. Okay, it's chosen arbitrarily, but once it's chosen, it must be fixed. Okay, so this is the angular momentum. This thing is called the angular momentum. angular momentum about the point O. Okay? So that's that thing over there, so time derivative of the angular momentum. And this here is the sum of the torques about the point O. And so what we have with this definition, we can write this equals this, we can write it in this form. Okay, we can write it as the sum of the torques. Okay, again, this is the sum of the torques about the point O. Okay, so that's that thing. Okay. Because if I choose, say the gravitational force, well, the gravitational force at this instant of time is exerting a torque on the airplane about the point O, which is r cross a downwards force, which is a vector out of the board. The torque is clockwise. If I chose my origin point to be up there, then r cross the gravitational force would be into the board. Okay, this way. Okay, so opposite direction. Okay, so it's very important to identify the point about which you are calculating the torque and the point about which you are, same point about which you are calculating the angular momentum. Okay, so then you get sum of the torques, that's this thing, is equal to the time derivative of this thing that we defined L. So this is dl dt. Okay, and again, this is the angular momentum evaluated about the point O. Okay, and so this equation looks a lot like this. This equation is the rotational analog of this equation. Okay, sum of linear forces is time derivative of linear momentum. Sum of angular forces, or torques, is equal to time rate of change of angular momentum. Okay, so that's completely analogous. I just want to say again that this equation contains no new information. Okay, this equation is all you need to solve the problem. However, this allows you to see a lot of really interesting aspects of that dynamics. Okay? Okay. So, very good. So let's think a little bit about, I just want to sort of illustrate why this is called angular momentum. Okay? So let me give you this, the simplest possible example is this. You have a point mass. Let's see. Yeah. Okay, so you have a point mass, m, and from this point mass, we're going to construct the simplest possible rigid body, our elemental rigid body, which is a point mass m connected with a massless rigid rod of length r, okay, to a pivot point. And we are going to imagine that this elemental rigid body is rotating about an axis that's perpendicular to r, the simplest possible situation. Okay, so this thing has an angular velocity omega pointing straight up. Okay, so that the angular velocity is pointing straight up does not mean the object is moving up. It means you put your thumb in the direction of the angular velocity omega, and your fingers curl in the direction of the rotation. Okay, so this rigid body is rotating. If you look from top down, it's rotating counterclockwise. Okay, and this mass m is rotating around in a plane which is perpendicular to omega. So we have a rigid body. We have this body here rotating in a horizontal plane like this, around and around. And the angular velocity is in that direction, which means it's rotating this way. Okay, that's the situation we've got. And what else do we need? So R is the vector. So now we're going to, in this situation, we're going to evaluate the angular momentum. What is the first thing we need to do? Oh, we need to evaluate the point about which we are evaluating the angular momentum. Okay, we need to pick that point. Well, the obvious choice in this case is right here. Okay, and so let's evaluate the angular momentum of this rigid body about that point. Okay, so what is the position of the mass m relative to that point? Oh, well, that's the vector r. Okay, that we've drawn right here. That's the vector r. Should be a vector. Okay. Now, as this thing whips around like this, of course, at any instant of time, it's got a linear momentum. That's this one over here, a linear momentum p. at that instant of time. And that P is equal to mv. Okay? So where v is the tangential velocity at that instant of time around that circle of radius r. Okay, what else? Okay, good. So now we need to evaluate the angular momentum that this rigid body has about the point O. Well, so what we do is we say, well, so it's a vector. We need to work out the magnitude and the direction. So the magnitude of the angular momentum about the point O. I'll be dropping this eventually, but initially I want to keep emphasizing over and over and over again. It's the angular momentum about our chosen point O. Well, what is that? Well, it's the position relative to the point O, the position vector r relative to the point O, times the linear momentum the object has at that instant of time. Okay? And so that's equal to the magnitude of the position vector r relative to the point O, vector cross product with p. Okay? And so that is equal to the magnitude of this vector r. Well, that's the radius of the circle r. The magnitude of the momentum p. Momentum is a mass-weighted velocity. It's the mass times the magnitude of the velocity, which is the speed v. So it's r times m times the instantaneous speed, tangential speed that mass has as it whips around. Okay? But then we remember, the tangential speed of a point on a rigid body is equal to the angular speed, omega, times the perpendicular radial distance from the axis of rotation. So v here is equal to r times the angular velocity. Okay? So this is equal to r, and v is equal to r omega. Let me write it slightly differently, because we never have enough room. So I'm trying to write things efficiently. Okay, so there's an r times v here. Oh, sorry, v is r times omega. Okay, and so we have an m. Yeah, let's write that first. We have an m, and then we have two factors of r squared. Let's put that in brackets. And then we have an omega. So mr squared times omega. And then that thing that we put in brackets, mr squared, well, what is that? Well, that's the moment of inertia for our elemental rigid body. A point mass m located a perpendicular distance r away from the axis of rotation will have a certain moment of inertia, mr squared. So this is the moment of inertia for our elemental rigid body, and it's multiplied by omega. Okay? So that's the magnitude of the angular momentum. So it's like mass times velocity. It's moment of inertia times angular velocity. And then the direction. So a unit vector in the direction of the angular momentum. Okay, that angular momentum about point O. Well, what is that? Well, the angular momentum is r cross p. It's a vector cross product. So we have to take the vector cross product of r and p. And when you do that, it's always helpful to move either p, the base point of p, to the base point of r, or the base point of r to the base point of p. So let's move the base point of p to the base point of r. So this is p over here. And so the angle between them is clearly 90 degrees. Okay, so when we work out the vector cross product of r cross p, well, it's a vector that's perpendicular to r and perpendicular to p, so it must be perpendicular to the plane in which r and p lie. And is it above the plane or below the plane? Well, r cross p tells you it's above the plane. Okay, and so the direction of the angular momentum is in the same direction as the angular velocity. It's perpendicular to the plane and up. Okay, the rotation is happening like this. Okay, so the angular velocity and the angular momentum point in the same direction, up. So a unit vector in the direction of the angular momentum is the same as a unit vector in the direction of the angular velocity. Okay, and so what that tells you is that the angular momentum of this rigid body, of our super simple rigid body here, is equal to, so the angular momentum of this rigid body, evaluated about the point O, okay, evaluated about that point, is equal to the magnitude times the direction. Okay, so it's equal to I omega times omega hat. Well, omega times omega hat, you can always take a vector. Any vector, any vector is equal to its magnitude times a unit vector in the direction of that vector. Okay, so here we have an omega times an omega hat. Oh, well, that's just the vector omega. Okay, and so we see that the angular momentum is just I times omega. Okay, and so in translational motion, we have the linear momentum is the mass times the linear velocity, mv. In rotational motion, say like this guy over here, we have the angular momentum, in this case about the center of mass, is equal to the moment of inertia about the center of mass times the angular velocity. Angular velocity is in that direction up in this case. Okay, great. So so this is completely analogous to P is equal to mv. Now, P is equal to mv. I want to sort of emphasize this small point here, that P equals mv is completely general. L is equal to I omega is not. Okay, I mentioned this a little bit before. The moment of inertia is not just one number. The moment of inertia is a matrix, a 3x3 matrix, because you can take a rigid body and you can rotate it about this axis, you can rotate it about this axis, you can rotate it about this axis, and so there are an infinite number of axes that you can rotate this object about. And the moment of inertia for rotation about those different axes is different. Okay, so the moment of inertia for rotation about this axis is large. The moment of inertia of this object for rotation about this axis is much smaller. Okay, so all of that information is contained in this moment of inertia matrix. Okay, so it's a matrix times the vector omega and so on. So it's more complicated in general. But in Phys 121, we will always be dealing with cases of high symmetry, okay, in which really we can just talk about one moment of inertia I. Okay. So anyways, so that's one thing to say. So that's how you can see why this thing is called angular momentum. You can see why it's called the quantity of motion associated with rotational motion. Okay? It's exactly analogous to mv, it's I omega. However, I want to stress that the angular momentum, the concept of angular momentum, is not limited to objects that are rotating. So L is equal to I omega is not the definition of angular momentum. The definition of angular momentum is R cross P. When we apply this definition R cross P to a rotating object like this, oh yeah, then it becomes I times omega. However, even objects in linear motion have angular momentum. Okay? So it doesn't have to be a rotating object. This is super important, or you can't solve like basic problems. Okay, so let me sort of illustrate this. Hopefully we will have enough room here. So I'm going to draw a plane, a horizontal plane. Okay, so here is a horizontal plane. Okay, and we are going to have an object in linear motion moving along that plane. Moving in that plane along a straight line. Okay, so it's going to be moving along a straight line like this, horizontally. It is going to like that. So at one particular instant of time, suppose that the object is right there. Okay, so that's our P at time t. And so this is our P. So we have an object with some quantity of motion, P, some linear momentum P at that instant of time. It's just drifting through space like this. There's no accelerations, there's no forces, nothing. It's just drifting through space along a straight line. Okay, and so we can define an angular momentum because there's a P, and as soon as we define an R, well then we can define an angular momentum. Okay, so now I want to stress again, the angular momentum that this object has depends crucially upon the point about which you are evaluating that angular momentum. Okay, so let me illustrate this. So suppose that we evaluate the angular momentum that object in linear motion has about that point O. Okay, so here's a point O. And so to evaluate that, well, we got to go R cross P. Well, what R? Well, the position of that object at that instant of time relative to that point O. So that's this vector. Okay, so this is, let's call this R, about point O. Okay? And so if we work out what is r cross p, so remember how you do this. You take, say, the base point of P and slide it to the base point of R. And then R cross P, well, that's easy. It's of magnitude R0 times P, and it's in a direction up, according to the right-hand rule. Okay, and so there's an angular momentum. So the angular momentum of this object in linear motion about the point O is equal to the position r about the point O, vector cross product with the linear momentum. Okay, and that vector r cross p is up, so it's pointing perpendicular to the plane. So what it's saying is that this object in linear motion has angular momentum. It has rotational oomph of motion in a quantity of motion in a rotational sense, which is looking down on the top of the plane counterclockwise. Okay? And now the reason why that's the case is the math doesn't know whether this object with linear momentum p at that instant of time is going to continue to move along that straight line, or whether it's attached with a massless rigid rod to that point and will actually end up doing this. It's actually moving in circular motion. So then this situation is identical to this situation. Okay? And so there's an angular momentum about the point O, which is up, perpendicular to the plane. Okay, so yeah, great. Now I want to stress the point that the angular momentum depends upon your choice of the point O. So let's go on the opposite side of the line, so down here. Let's choose a new point. Let's call it O prime. Okay, and so we need to work out what's the angular momentum about the point O prime. Well, we need to work out r cross p. Well, what r? Well, the position of the object relative to the point O prime. Well, that's that vector, okay, at that instant of time. So this is r, the position about relative to the point O prime, okay? And p is that. So we need to work out r cross p. Well, what is that? You can take the base point of p, slide it down to the base point of r, and it's easy to see, oh, RO prime, vector cross product p, is a vector which points down. It's perpendicular to the plane, but it's down as opposed to up. It's in the completely opposite direction. Okay, so this is, let's make it about the same length. So this here is the angular momentum of that object in linear motion about the point O prime, okay, which is RO prime cross P. Okay, and it's in the completely opposite direction. So I stick my finger, what is the direction of the angular quantity or the rotational quantity of motion? Well, I stick my thumb in the direction of the angular momentum, which is down, and my fingers curl this way. So looking down from the top, we're talking about clockwise rotation. Okay, so it's clockwise rotation, okay, like that. Because again, whether you're talking about an object which is moving with linear momentum like this at this instant of time, or is actually attached to this object, it's attached to that point with a massless rigid rod, okay, and is actually going to be moving around a circle this way, looking down clockwise, okay, it's the same answer, okay, great. So what else? So looking down from the top, if this were a rigid body, the rotation would be clockwise. Looking down from the top, if this were a rigid body, it would be counterclockwise. Okay, so the angular momentum depends upon the choice of point about which you are evaluating the angular momentum. Let's choose a third point. Let's choose this point right over here, which is along the line along which this massive object is moving. Okay, it has some momentum. So let's call this point O double prime. Okay, our third choice of origin. So then we evaluate the angular momentum, r cross p. Well, what r? Well, the position of the object relative to the origin O double prime. So this is r O double prime. And so we work out, well, what is RO double prime cross P? Take the base point of P back to the base point of RO double prime. Obviously, these vectors are parallel, and so the vector cross product of parallel vectors is 0. So the angular momentum of this object in linear motion about any point lying on the line along which it's moving, LO double prime, is equal to RO double prime cross P, which is obviously 0. Okay, so the angular momentum is about any point along this line is 0. Along any point on that half of the plane, it's up. Along any point on that half of the plane is down. Okay, but definitely objects in linear motion can have angular momentum. That's super important, or you can't solve angular momentum problems, conservation of angular momentum problems. The next thing I want to point out, final thing I want to point out, is this is the momentum of the object at this instant of time. Sorry, this is the position of the object at this instant of time. Later on, it's going to drift over to here. Okay, and there'll be some momentum, P, same P. There are no forces acting. The momentum remains constant. Okay, so later on, the object is over here with the momentum P. Let's evaluate the angular momentum of this object at that point with momentum P about that same point. How do we do it? R cross P. So the R now is a vector pointing from that origin to the point of the to the location of the object at that instant of time. So let's call that, instead of little r0, let's just call it capital R0. Okay, just to have a different letter. Okay, so great. So how do we calculate that? So later in time, the angular momentum, so later in time, the angular momentum of this object about the point O is equal to this R, okay, which is R0, okay, vector cross product with the same P. As there's no forces, momentum is not changing. Okay, but that R0 is the same thing as, let's call this vector, the vector pointing from the old position to the new position. Let's call that, I don't know, D. Okay, so R0, the vector from there to there, is equal to, adding tip to tail, the vector from there to there, R0, plus the vector from there to there, D. Okay, so big R0 is little r0 plus D. Okay, vector cross product with P. Okay, what is D cross P? Well, D is in that direction, P is in that direction. They are parallel vectors. The vector cross product is 0. Okay, and so this results in R0 cross P, which is exactly the same as what we had here. Okay, so it's saying that the angular momentum that this object has as it moves along that line about that point does not change. It's constant. Why is that? Well, because there's no torques acting. There's no twisting forces. In order to exert a torque, you need a force. Okay, there's no forces acting, so there's no torques. No torques means the left-hand side is 0, means that dl dt is 0. That means L is constant. Okay, so as this object moves along that line through space with a constant linear momentum, the angular momentum that it has about that point is always the same, whether it's here or here or here or here or here. It's the same values it has right here. Here it's easiest to calculate, R0 cross P, that's easy, but it's the same anywhere along that line. Okay, and in order to see it, we can do this kind of a calculation, or we can also do this kind of a calculation. This is a triangle. Let's look at that triangle from the top down. Okay, so this is a right angle in that triangle. So from the top down, we have R0 is the length of that side of the triangle. D is the length of this side of the triangle. And big R0 is the length of this side of the triangle. Big R0. Okay, so big R0 is a function of time. Okay, as the object moves further and further down the line here, R0 gets longer and longer and longer. Okay, the hypotenuse gets longer and longer and longer. Okay, and P, there's an angle here. So the angle between, we work out R cross P, it's the angle between R0 here and P. So that's this angle phi, which is also a function of time. That's this angle here, phi of t. Okay, so if we were to work out what is the cross product, well, the cross product, R0 cross P is the magnitude of R0, running out of room, the magnitude of R0 times the magnitude of P times sine of the angle between them. Okay, so R0 and phi are changing with time. R0 starts small, and then it gets longer and longer and longer. So R0 is increasing with time, but the angle phi is decreasing with time. So that the product is constant. Well, what is that constant product? Well, the hypotenuse times sine of the angle phi is R0, which is constant. That's R0 times P, which is the same magnitude here, because at this instant of time, R0 is perpendicular to P, and the magnitude of the angular momentum is just R0 times P, magnitude-wise. Okay, so so it's good to be able to think in terms of vectors like this. So it's also good to think in terms of triangles like that, and so on. Okay, but at the end of the day, we have that the angular momentum of this object in linear motion, when there are no forces acting, no torques, remains constant. That's a consequence of conservation of angular momentum, which we will talk much more about. So the crucial thing I just want to leave you with is I want you to just remember that if we have an object, its position is relative to some point O. Its angular momentum is relative to some point O. It's R cross P. Okay, that R cross that P, that R is relative to the point O. Okay, and the torques that are exerted on that object. Okay, well, those are torques about the point O. Okay, so all three of these things depend on O, depend on the choice of origin point O. Okay, but regardless of which choice you make, okay, you just pick a choice and stick to it, this equation will be true, okay, as long as you stick to that point O. And usually there are convenient and obvious places to make a choice where to put O, okay? That's just part of the art of solving these sorts of problems, okay? And you'll sort of get familiar with that as you go along. So anyways, angular momentum. So it's basically the quantity of motion associated with rotational motion, okay? Instead of mass times velocity, it's moment of inertia times angular velocity. But super importantly, objects in linear motion can also have angular momentum about a point that's not along the line of motion, down here or up here. They can have angular momentum. If it's up here, the angular momentum is counterclockwise. If it's down here, the angular momentum is clockwise. Okay? Very good.